Hello, this is Yan from the University of Michigan, and in collaboration with the University of Florida and the Northwestern University, I will be presenting our work of facilitating the decontamination of N95 masks with wireless sensor technologies. I will also share with you the design challenges and lessons learned in order to better safeguard our society from future pandemics. So N95 mask shortages have been a persistent and enduring problem in almost every significant pandemic. In just about half a year ago, the world was still experiencing a global shortage of these masks in face of the COVID-19 pandemic. The abrupt and fierce increase in the demand for the masks quickly depleted our supply chain and forced the public and healthcare workers to reuse their masks. However, the reuse of the masks poses severe risk of infection because of the potential pathogenic agents present on the masks, especially for frontline healthcare workers using the same disposable mask over multiple days when treating COVID patients. So to lower the risk of infection, the masks need to be properly decontaminated before they can be reused. However, proper decontamination of the masks is actually difficult. Different decontamination methods have been proposed, but most of them suffer from various problems. And out of those, moist heat contamination was recognized by the US CDC as one of the most promising and accessible methods for emergency use in under-resourced hospitals. So basically, moist heat contamination requires the masks to be placed in an environment of certain temperature and relative humidity for a certain period of time, and each mask is held in a sealed rigid container with a wetted paper towel to maintain the humidity and to avoid cross-contamination between the masks. The good news is that hospitals usually already have such commercial heating devices that can satisfy the requirements, And however, we were still in lack of a scalable way to do constant per-mask monitoring of the temperature and the relative humidity in each container to ensure that the decontamination condition for each mask is satisfied. And this is because the commercial heating devices suffer from problems such as non-uniform heating. In addition, operational errors can also lead to unpredictable humidity leakage from containers during the process if the containers are not properly sealed. And these can all cause decontamination failures without being detected by the heating device built-in sensor. And furthermore, commercial heating devices do not provide a feedback control loop by considering the temperature and humidity readings in each container. So there is no way to maximize the number of masks that can be successfully decontaminated. To tackle these challenges, we thus developed the VeriMask wireless sensor platform that consists of an Android monitor application and wireless sensor nodes. And each node is associated with one mask in order to accurately monitor the environmental conditions of each mask to ensure the safety of this process. The Android monitor application provides automatic per-mask verification of these decontamination conditions and enables a human-in-the-loop feedback control with the throughput maximization algorithm we developed. The nodes and app communicate with each other through Bluetooth low-energy advertising, which ensures scalability. And we also carefully characterize the loss rate of critical sensor readings and thus guarantee the safe wireless transmission using BLE advertising. In addition, the number of successfully decontaminated masks in a decontamination cycle is affected by some key factors like the set heating device temperature and the moist heat decontamination process time. So considering the throughput maximization as a 2D optimization problem, we developed an algorithm that converts it to a 2D grid search problem by allowing the operator to conduct a profiling decontamination cycle. So the algorithm will automatically adjust the sensor reading curves in the profiling cycle to predicted curves under different device temperature and cycle time, and thus to find the combination that generates the largest number of successful masks in a given time. For example, the figures show that with the thermal chamber as the heating device, we increased the number of successful masks from 8 to 11 in a 20-container test, and from 9 to 11 in a 15-container test. And interestingly, our tests also show that more containers in the heating device does not necessarily lead to more successful masks. And the reason is that containers could block the hot airflow in the heating device and thus cause more serious non-uniform heat distributions. And this thus also verifies the necessity of having the VeriMask platform to monitor and optimize the whole decontamination process. We did extensive tests in both the lab and clinical setting, and results show that VeriMask is able to reliably detect various kinds of decontamination failures. For example, these figures show the relative humidity in a leakage and no leakage case, and VeriMask was able to detect a decontamination failure when there is humidity leakage, for example, due to improper container sealing. Finally, designing and manufacturing VeriMask during the pandemic taught us valuable lessons of emergency response design. First, such designs should be prepared long in advance to avoid being delayed by the disrupted supply chain and strict clinical access regulations in the pandemic. And second, designers should plan for the worst-case scenario and design for modularity. The pandemic could render the electronic devices out of stock for months, so the designers should thus avoid assuming adequate supplies for emergency design and should even consider candidate components even from the design phase. Furthermore, mobile computing researchers should engage early with medical professionals and the end users to have communications that enable more efficient and down-to-earth specification derivation and also help avoid over-optimization. Based on these lessons, we summarized the general emergency design criterion and guidelines, and we would encourage the readers to refer to our paper. We make the VeriMask design open source to help researchers better prepare for future crises, so please feel free to contact our team about the open source project. Thank you.